this here. Yes. Right. Another important thing that we discussed when I introduced the non-functional aspects and the CAP theorem is the aspect of standardization. An important thing about the relational solution, because it's been around for a long, long time, is that everything is standardized. So if we learn SQL3, if we have and know strategies about the way internally the DBMS works, this happens for any relational DBMS, and this is very important with regards to the expertise of your engineers, because this means that nobody has to further study or get acquainted to the systems. Any system in the commercial market works in a standardized manner, and your assets can work with these different solutions. And then, of course, well, this comes from, this is for historical reasons, SQL solutions or relational solutions address in a very smoothly manner reporting aspects, and that's something that you studied in advanced databases. You learn how to deal with data warehouses, and data warehouses, for example, are solutions that are quite devoted to reporting, to aggregation, and existing systems give a lot of facilities and tools in order to deal with this type of exercises that people in organizations have to do. Yet, there are some pitfalls. You have had the experience of this, even if the backend of a relational system is distributed, is a cluster or whatever. The idea is that you only have one entry point towards the system, even if behind it does a lot of optimization of resources, etc. And this abstraction and transparency with respect to what works behind is not very interesting when you get out of the box, in fact. So when your requirements are no longer those of the payment charts and of a very structured solution, then not exhibiting the infrastructure that is behind running the system has a lot of pitfalls. That's one thing. And the other thing is that if you have anyway a cluster behind, the administrator of the DBMS has to do a lot of tuning in order to make sure that the system exploits in an optimum manner the cluster on top of which it is installed. And this is an enormous pitfall when we deal with collections as the one that have been emerging out of the big data trend. And so raised NoSQL solutions as alternative facilitated solutions that, in fact, if you refer to the three-level architecture of the relational solutions, they have a very thin logical level, and that makes you work in a very close manner with the physical level. So the physical level is exposed with a very thin logical level, and you as a designer and programmer of database solutions, you work very close with these two levels. Another important difference that you have to bear in mind is that the separation between data management and programs is no longer assured. Okay, so you lose this facility, and this has impact on your time to market. But anyway, these solutions are interesting when you do not want to devote a lot of time in designing the database, when your data structures are not systematically systematic with the data structure that they provide. So you need flexibility in terms of the modeling of your data, and the NoSQL solutions promote this kind of philosophy. You invest very little time in the design of the database, and you invest a lot of time in the exploitation of the database. That's something, we all have to pay at some point something with respect to the solutions. And so another thing is that even, well, you have seen with MongoDB now that even if there is an interest in providing more or less declarative ways of expressing queries, finally, they are not declarative as in SQL. You have to bear in mind which are operators, which are attributes, etc. And this makes the expression of queries a little bit complex in comparison to the declarative approach of SQL. And then another thing that we saw is that with respect to non-functional properties, not every system and not every application needs the guarantees of ACID transactions. And so what the non-functional solutions, non-SQL solutions provide is an alternative to ACID transactions that is called base, no? And we discussed that with respect to the CAP theorem, and we said that anyway, these properties are enough when you address applications that need intensive reads and writes, but do not want to care a lot about concurrency control and about the properties and guarantees that are ensured by relational solutions. And another thing is that anyone can invent his or her data model and design a data management solution and put it on the market. And so normally what we have seen is that the families that can be identified with respect to the data models are variations of tabular representations that go from the very simple ones, which are key value solutions, towards more complex ones that go towards document-oriented solutions, and that we saw in practice. And then there are other variations like the columnar families that we are not going to study in this course. And then the social networks emerged with their huge volumes of data and their huge requirements to do analysis and exploration on their data, and the graph database solutions came back to the arena. Graph database solutions were very popular for dealing with electronic science applications, but they remained like in the ivory tower. No, this was for mathematicians, for experimental scientists that wanted to understand biological data, social data, this kind of problems, but they remained in their ivory tower. This was not the market. But suddenly we had these social networks emerging, and afterwards we had a pandemic in the world, and graph databases emerged as interesting and promising solutions, not only for the ivory tower, but to the today applications. And this is why we're going to zoom into the type of solutions that are here today in order to deal with graphs. So we are going to do more or less as the way we did with MongoDB. I'm going to introduce the general concepts that you have to remember, in fact, about graphs, because one particular thing that is that in the computer science education, we are quite acquainted with graphs. This is something that we learn from the beginning of our education. So the idea is that you unbury your old initial courses on graphs, and you put them to the service of data management. So the idea is that a graph database will provide graph structures consisting of nodes, as you know, edges and properties in order to represent and store data. Can someone tell me how do we represent, what is a data structure that we use in order to represent graphs? At least one.
Matrix.
Matrices. And another one, it's a variation of matrix. Linked lists. With a variation of a linked list, we can also represent graphs, which means that this is very good news, because data structures, matrices, are basic data structures that cope very well with the way we represent data in memory and in storage, in disk. And so the solutions can work in a very smoothly manner with respect to the basic programming solutions that we know. Exactly. Okay, so normally, as you remember, nodes are of similar nature. They can represent objects, they can represent any entity in the world, and programmers are familiar with them. And then we can associate to the notion of node a set of properties that describe this node. And this happens also with the edges. You can have edges, and you can also associate properties to the edges in order to precise the type of relation that connect to nodes and or other associate weights, etc., and add information about the conditions in which two nodes can be associated together. And so the intuition is very nice. It's also very nice because we can draw it in a very intuitive manner, and almost anyone can understand at least the very principle of graphs. Then things become less simple, but initially we're happy to see the rounds, the balls and the edges, and figure out what's going on with respect to our data. So once you have it, what will a graph database will provide? Well, it will provide the adapted data structures in order to represent internally your graphs, and the necessary indexes to organize and ensure rapid access to the data, and this working with the storage support, and then the right operations in order to explore the graph. So that's what you expect from a graph database management system. The representation of your nodes, the internal representations of the nodes, the indices that you can associate to the graph, and the kind of operations that you can use in order to explore the graph, which corresponds to the knowledge model of any database. So this is not very nice, but you can see. So as you can remember, another interesting thing with respect to graphs is that we come back to a mathematical model. And when we have control under mathematical terms, this is very comfortable because we can reason about performance, we can reason about the cost of the operations that we can have, and therefore we can also guarantee some performance of the management of the graphs in a data store. So normally, as you remember, you can represent a graph with as a tuple of two elements, a set of two sets, the set of nodes and the set of edges. And we can call them edges or we can call them relationships. And as you remember from your courses, the edges can be directed or undirected. So first thing that you have to ask about a graph data management system is which are the types, which are the types of nodes and the types of edges that you can use in order to represent your data. So as you remember, an undirected graph, they just have no orientation, and so there is no notion of order of the pairs that you can identify, the pairs of nodes that you can identify within the graph. All nodes have the same object type, and all edges have the same relationship type. Okay, so that's the way you deal with undirected graphs. Then directed graphs, on the contrary, can have, well, the edges have directions. All the nodes are of the same type, and then you can define whether whether the direction of your relationships is in one way or in two ways, in a very intuitive manner. Of course, I'm not teaching formal aspects of data management systems. And what do I do with this? I can do a lot of things, because the first thing that I have to decide is which is the best graph data model that I can use in order to represent a mini world, a set of a data collection. And for example, you and I that are quite acquainted with social networks can identify, for example, that let's consider the case of Facebook, when you have the graph of contacts that we can have on Facebook. What happens is the nodes represent a contact, so a person, and then a person can be friend of another person, and the relationship is symmetric. When I'm a friend of you, you are my friend. Okay? And the only type used in order to represent a contact is the notion of user. Okay, so with this very simple graph model, we can represent the network of contacts within this social network. In the contrary, if we go, for example, to Twitter, this is a little bit different, because of course nodes represent always a user, but in Twitter what happens is there is a notion of follow. So me as a user can follow another user, but this is not symmetric. The target user does not necessarily follow me. So we can have situations in which I follow someone, but the someone doesn't follow me, or I can have symmetric cases in which both of us follow each other. So you have a graph where sometimes your relations are in one sense or in both senses. So you need a more complex graph model in order to deal with this database, with this set of contacts. And then, of course, well, what happens every time that we invent something is that, in fact, we realize that we need the advantages of a lot of things, because the world is never symmetric and is never stable. So normally what we use is a mixed graph that accepts different types of relationships, and that can have an indirect and direct edges to connect the graphs. And sometimes there are other restrictions that we impose in order to facilitate the life of the graph traversal, of exploring the graph, is that something that we can decide is whether a node can be connected to itself. If we allow this means that when we will explore the graph, we will have hard time in order to deal with this exploration, hard time in terms of computational cost. And as I said, the good news is that in advance, we can prevent this situation and provide alternatives in order to avoid this cost without really going into the matter and implementing something. So normally what we have is, what we have to think is whether we are using multigraphs, whether our relationships are of the same type or not, whether the nodes should be of the same type or not. And according to this, we decide which is the best graph model that works for us. And if we are choosing a graph data manager, what we have to go and see is which are the characteristics of its graph model in order to decide whether that system A or B are which is the most appropriate in order to deal with our data. So this is what it says in nice terms in this slide. The case of the social networks, particularly Facebook, is quite evident because some of the relations are just contact, but you can tag the relation with a type. And you can say, I am contact with this person, and this person is my mother, or is part of my family, or is an acquaintance, or is a colleague. And there you see you have not only the relation, but you give types to those relationships. And you can go further and say, okay, I can be a person, a user, who is a person, or I can be a user that is an organization, or I can be a private user, or I can be a public person who is a user. Okay, so you can have different types of nodes representing the different types of users. Okay, and if you are dealing with all these, well, then you need a graph model that lets you do this kind of reasoning and of representation. Here is another example regarding Twitter. Some relations are blocking. For example, I want to block this person who is following me. I can reply to a person, to a contact, etc. No? Also, I can have different relationships representing the type of interaction that two nodes, two users have between each other. And again, the users can be of different types too. Sorry. So there used to be in the time of no time before before Twitter. You might not know that time. There was, for example, an alternative called LIS. And LIS, you could follow contacts. You could contacts could be elements, could be devices, or they could represent people, and you could like them. You could want something from the devices. You could connect to the devices, and so they mixed the physical devices with the users, and you could have like a kind of social hybrid social network with devices and people, etc. So that was another aspect. And then comes the notion of property. You can have the notion of a node representing a user just like that, or you can add properties to that node. And as I said, to the relation, for example, in the case of Twitter, you can have the ID, how many followers the person has, who follows the person, and since when the person is part of the network. And then if you represent a relationship, you can say that A follows B since a date, okay? So normally in almost all graph data managers, you have the notion of property graph, in fact, because you need a lot of expressive power in order to represent a lot of data collection. So this is normally the way that the kind of model that is adopted in order to deal with graph databases. And so again, you can go further and represent much more information of your social network, adding these properties to both the nodes and the relations. And this is it. This is what you have to bear in mind with respect to the graph model. So it's not nothing, it's not rocket science, it's quite intuitive. And then once you have remembered these notions in order to be used to represent your data bases, then you have the operations. And normally, when we deal with graphs, in fact, what we do is we explore the graph, and you remember that in our studies, we learned that this exploration of the graph is called graph traversal. So the game here is how to best traverse the graph going from one node to another uh, with specific constraints, without revisiting nodes twice, without going to the same, losing ourselves, going around and around, going through the same path and not reaching another node, etc. Okay, so when this is associated to a graph manager, the traversals that you can perform throughout a graph are queries. Okay, so they become queries. Some queries and some traversals are represented as operators, and others are expressed as expressions, are kind of regular expressions, okay, in order to describe the characteristics of the path of the traversal that you want to follow in order to reach a node starting from another, okay? And as you remember, the problem is that there is no start, it's not a tree, no? So you never have the root. Every node is an entry point throughout the graph, okay? And this is challenging with respect to these traversals. So this is the right definition. To traverse a graph is to process every node in the graph exactly once, as I said, because otherwise we fall into overhead. The two most common traversal patterns are, as you remember, that's something from the beginning of our studies, is breadth first traversal and depth first traversal. And here we meet for the first time maybe the fact that given an operator, so breadth first traversal or depth first traversal, you can have many different algorithms solving this operation, implementing this operation. And I don't know if you are aware of this, but in the relational model, it's the same. For example, join, select, etc. There are many different algorithms that implement these generic operators. And the system chooses the one that comes first with respect to a lot of variables internal to the system. The only difference is that the system hides this, and here we have to think about this. So the first thing that many graph managers at least let us know or let us choose is which technique we want to apply in order to traverse our graph, first of all. And second, which is the algorithm that we want to use in order to apply, to implement this technique. The very principle anyway to both of these techniques is that for each step, the traverser moves from to its adjacent vertices, and you repeat this until n times until you fulfill a termination condition. Okay. So you see here the principle, there is no longer a principle of termination. You have to define both what you want and the terms in which you want to traverse the graph, and at what moment you want to stop. Okay. So if we go back to the social networks, for those that have forgotten a little bit about graphs, the question is, for example, if I decide I want to publish a post, and I can say who can read it. And imagine that I choose anyone. At what moment, until which depth, will the algorithm stop letting see my message? My friend, my direct friends, the friends of my friends, the friends of my friends' friends, etc. Okay, so there is always a point in which the function has to have a termination condition. Otherwise, imagine in Facebook, anyone could see at a very in a very deeply manner, and this would cost enormously. Okay, so normally you have to have this condition that will stop the system go through the whole graph, because this is very costly and you are not sure that it's necessary. And here we come to another important difference with respect to the expectations that you can have with respect to the results you obtain from a query. In the relational solution, we are used to be sure that we will get, for a given query, all the data that fulfill the conditions of the query, all the data that are stored in the database. No one will be missing. In the case of a graph, this is not completely true. We might have partial results given a query, depending on the way we establish this condition. Okay, so it is up to us to define the completeness, the degree of completeness of our results. Okay, and it is very rare when we are dealing with huge volumes of data that we get a complete result. It's more or less like uh, having synchronizing with the philosophy of search engines. Okay, in search engines, you are never sure that you have the complete answer. You are never sure that you get all the documents that fulfill your query, but you accept this and you have a lot of them, and normally you don't even explore the whole partial result that the search engine provides. We just explore the very first. Well, in this case, it's the same principle. It will provide a partial result, some result, and then it will be up to us to define whether we want to go further or not, and express this in a query. Okay, so questions until here? Right, no questions? So what we will do, not today, but tomorrow, is we're going to see how does it work in a practical example. So what we will do is use a very popular graph database management system called Neo4j. And in fact, we are going to adopt more or less the same principle as with Mongo. There we will connect to a cluster that provides, to a cloud that provides a cluster of Neo4js. And then we will see how it works, or how do we create graphs, and how do they look like, and the type of operations that we can use in order to explore them. And in general, these solutions tend to have a declarative language in order to, semi-declarative language in order to express the queries that looks a lot as, have you learned Prolog, or a logic language, programming language?
Yes, really, a little bit.
Okay, so the queries look like that. Okay, and this is not surprising, because that you probably have not studied, because it's quite technical with respect to databases. In relational databases, you can also reason about logical expressions of SQL. Do you remember that there is the relational algebra, and there is the relational calculus? Well, when we think about relational calculus, we opt to a logical expression of queries, and there is a quite popular formal approach to express queries called data log, which looks like more or less like, you have the rules like in Prolog, and you express your queries like that. So in graph databases, the query language that they propose look more like Prolog statements. So that's something that we will do tomorrow. And this will be important also in order that you compare, okay? And that we compare together the data model, the possibilities, the expressivity of the queries, the possibility of whether they are equivalent or not, or in which conditions one is more adapted to something than the other, okay? Because this is not immediate to see for anyone, not just for beginners of NoSQL like we are, but for any person that wants to address this problem. Okay, so graphs stay a little bit in their box, while tomorrow we go for them, the whole session. And then another thing that we have to discuss is this problem of choosing a system or another for addressing a problem. The truth is that for a given application, you need different data management solutions in order to deal with the data. Okay. And so the idea is that you use multi models in order to manage all this data. And I think that in advanced databases, you saw multi-databases, so distributed databases. So this is more or less the same principle, but instead of having many relational systems behind dealing with the data, what you will have is different NoSQL systems dealing with portions of your data. And so first question is, how do I fragment my data to decide which goes to a graph, which goes to a document, and which goes to a key value, or to document solutions with different characteristics? And then how do I make sure that I query this set of data, and how do I manipulate them with different guarantees? Okay. So the generic term to refer to NoSQL multi-databases is called polyglot persistence. So the idea is that you have several data stores in the same, for the same system, for the same information system. So many different things to consider. Well, of course, the deployment is much more complex because you deal with different systems, with different APIs, with different principles of use. So that's a quite delicate aspect to consider. It is also complex with respect to updates, okay? Because if you have, for example, you decide that you have different data stores behind, but you provide only one homogeneous interface for final users to interact with the data, the problem is that people will update some item, and this item can be splitted into two different data management solutions. And you have to deal with these aspects, and the person shouldn't see what are these challenges and how they are implemented. And of course, there is a problem. We have seen that each system duplicates the data, so there is a problem to deal with respect to duplication, and of course, with respect to consistency, since different consistency strategies are implemented in the different solutions that compose the multi-model. But this is what happens in almost all organizations today. So just to land into the concepts, polyglot persistence is using multiple storage technologies chosen upon the way data is being used by individual applications. So the idea is that, remember that at the beginning of the course, I said, since data, you are dealing with volume and velocity, and transformation might create a lot of overhead. The idea is that you respect the data format of the data, and do not transform it. Okay, so you look for the right data structures that can be used to represent the data without any transformation. So the idea is that within an organization, you will have data that is quite structured and that is interesting to be modeled in a tabular and a structured manner, for example, relational or a tabular manner. And then you have documents going around the organization, and those documents, it's better to use a document solution. And then you can have, for example, these connections and representation of networks. So you use a graph in order to represent such a thing. And you combine everything. In fact, polyglot persistence has its twin aspect, which is polyglot programming. This happens again with programming. Instead of only using one language to implement the whole application logic of a solution, the aspects that go better with functional aspects, you implement them in a functional solution, for example, in JavaScript or in Python or whatever. And then other aspects that are more low level, for example, dealing with matrices, there you prefer C or C++ to implement them, and then others you prefer Go to implement them, etc. And so you combine many different languages in order to implement your algorithms and your operations depending on their characteristics. Well, in the same way, you will have a polyglot persistent solution where you deal with several data management solutions. And there you have a mess, because this is interesting in terms of being comfortable to not do a lot of heavy lifting at the beginning of the system, but then the maintenance is another thing. Okay, because, well, if you think in terms of engineering assets, you need engineering assets that are comfortable in changing programming language, that are productive independently of the language they program in. And then maintenance, you have to understand the code implemented, written in many different languages, and this is a complex thing to do. And if you add the polyglot persistence situation, there you have a challenging thing to address, but we are not scared about such kind of challenges, and we do them independently of the complexity. And yes, there is, well, this type of solution, in the contrary to other solutions, emerged from industry. Okay, so NoSQL and this polyglot persistence story, in fact, it was people that were dealing with applications, etc., that suddenly realized that they needed this type of approaches in order to deal with their problems. And so they started to combine programming languages, data management solutions, and at some point they declared that this was a software engineering strategy to be adopted in order to develop systems. And a very nice book, it's old now, but it started when more or less at the beginning of the history of NoSQL, is the one written by Fowler. The reference is down there. It's NoSQL distilled, so it's a brief guide of a polyglot persistent solutions. And so he describes the challenges and the use cases that he addressed, and where he applied this approach. So for those that think that at the university we do not see real cases, we do. Here is a real case, and we are having a look in the university at this. Okay, so it doesn't come from theory. And how does it look like? Let's have an example. Consider the classic retail web application, e-commerce. Okay, so everyone today has implemented an e-commerce solution. This is the first project that someone can do in undergraduate studies. No, so what happens in such kind of application? Well, let's see which are the data that we have to deal with when we implement such application. For example, first thing that we will have to deal with is the users. Okay, so we are going, let's consider that we have declared users as in normal e-commerce applications. We will not complex the situation and accept guests. We are going to assume that every user that buys in our retail web application is identified. So you have the information about the users. You have your financial data to deal with the purchases, etc., and buys of catalog, etc. You have your product catalog we're going to sell. Since we want to know whether the application is providing return of investment, we need to have reporting. We have also to have not only reporting, but analytics that will tell us, for example, to predict whether it is good to have new products, at which point it is interesting to add new products to the catalog, maybe in some region of the world and not others because of the characteristics of the users, etc., or because of taxes conditions. It's better to provide some strategies. Then we also need to deal with user activity logs, because at some points, imagine that there is an unconnected user, etc. So we want to make sure that when the user comes back, she or he doesn't lose her choice of products, and so in order to provide a better service in our application. Since we want to compete with Amazon, we want to retain the attention and keep the attention of our users. So out of the history of purchases of our users, we can also recommend products that might be interesting for them. And finally, we have, of course, the data associated to the purchase process. So we will have the notion of shopping cart, where that contains products chosen by a user with their price, and then, the classic operation of having the chart and validating that the things are available, and then doing the payment protocol. Okay, so this is only the data that we might need to deal with in this kind of application. But as we learned until now, it's not only about the data characteristics, but it's also about the guarantees that we need to associate to the management of this data. So, for example, if we think about user sessions, we might need to have rapid access for reads and writes, no? So that new customers can come and declare themselves, etc. And we also need an agenda of clients, so we want this information to be durable. Then, for example, the catalog. In fact, we are not going to add every second new products to the catalog. Okay, the catalog is something that is more or less stable. But if we are lucky and that we have a lot of clients, the thing that happens is that we need to ensure very agile reads of the catalog. Okay, not like Walmart, where you click and you wait 3 minutes in order to see the next object. No, we need to show our items and the descriptions, etc., in a very agile manner so that we do not lose clients. So very frequent reads and a very few writes. And if possible, we would like to be very friendly in terms of exploring the catalog. Okay, so probably we will have queries expressed either in keywords or preferably in natural language. So that's for the products. Then reporting. Well, reporting is reporting. So there we might need to have a structured representation of the way our e-commerce application works, and then create weekly or monthly reports to know how we are going. Then, since we are very popular and we sell a lot, then we might need we might collect a lot of data, so we might need clusters in order to do analytics for that and for the user activity, because we can imagine that we have a lot of users. Then the shopping cart is a very nice aspect to think about, because you need locking. When a person chooses an item, the item in the catalog should be blocked, and we have to decide on how long are we going to block the item so that other people can see whether they are interested in the same product. They can see the different items of existence of the catalog, but that they do not block each other. So we need concurrency control on this, and we also need fault tolerance, because if in the middle of the purchase process we lose connection, or there is a fault, or etc., it would be nice to let the user retrieve the last state of her shopping cart when we come back from recovery, for example. And if we are in the payment process, we would like to ensure that the payment is not done twice because of a fault. So there we need much more non-functional guarantees to ensure only for this shopping cart. Okay, you see, so different data, different representations, different guarantees required. So question is, do we use one solution, one tool to manage all these, or rather we treat these different elements separately as one system, and we adopt different data management strategies according to their characteristics, and then the whole application will have these different solutions but integrated in a whole information system. Okay. So this is the principle of applying polyglot persistence in such kind of solution of problem. And then, as you can see, the very classic web application, e-commerce application, already proposes these challenges, these data management challenges, to be considered and dealt with in its construction. And as such, you can imagine, I'm sure, many different types of applications where you have this variability of requirements and where a polyglot persistent solution might apply. For example, I usually teach for industrial engineers. And for example, in manufacturing, and I have had also projects in aeronautics. And there, well, of course, it's everything. You have different agencies, you have different providers of products, of clients, etc. So in such kinds of settings, you deal, in fact, with many different solutions. For example, the catalog and things like that are very structured and do not move enormously in terms of data structure, but then they are normally dealt with relational databases. But others, for example, all the orders, for building a product, let's say a car, many different documents are produced in order to order the components of the object, and they are associated to different providers, etc. So all this documentation, and you have to track, etc. So key value or document databases are interesting to be used. And then if you want to see the whole the way the shop floor of the company works in a very generic and intuitive manner, then, for example, the graph database can be a nice solution in order, to see the relation between suppliers and orders, the orders and customers, the orders and payments, the orders and the products you want to build, where they are located, if the different parts of the product, for example, are constructed in different locations, which is the relation between the portion of the product that you want to deal with and the location in which this part is constructed. So in this kind of systems and context, polyglot persistence is also a very nice way and practical way in order to deal with the data. Other examples in energy, and of course in science, you have a lot of them. So this is why it's important not only to consider these different solutions, but know in practice how to put them together and build realistic solutions. Now, there are some things that can guide us to address a problem in terms of polyglot persistence. First of all, is which projects are candidates for this. Okay, there is no point of complexifying something when it's not necessary. Okay, so that's the first thing. So you have to think about when it is strategic to have such kind of solution. And you have also to consider whether you have constraints in terms of rapid time to market or data intensive app requirements. Okay, so lots of data, high availability, lots of traffic of reads and writes, complex relationships. So when you have a combination of these, polyglot persistence might be a solution under the condition that you have, of course, the right group of engineers that can deal with this. Okay, but here we are assuming that you have the advanced expertise in order to deal with such kind of aspects. Um, so what do I have to say here? Yes. Now there are if organizations have to deal with these kind of solutions, at some point in some of the other sessions, I said that the choice of NoSQL systems has also to deal with the type of organization you are working in. And I said for very pyramidal organizations, maybe, and particularly polyglot persistence, is not a very well adapted solution to use because you have different data administrators. They have to make very important decisions, low-level decisions that in a pyramidal organizations always go to the upper levels of the organization. So if you want to wait, you have to wait for an authorization of the president of the organization in order to decide whether you are going to add a node to a cluster of your MongoDB because something there, this is not the case, or that you are going to install now Neo4j because part of the data are adapted to this kind of solution, and you need to ask, as I said, the president of the organization in order to accept this. This is not your solution. Okay, it's more adapted to flexible horizontal organizations, startups, for example, where people make decisions and go for it, and they address these technical aspects, and they have the power of deciding alternatives, etc. So another thing is that you have to deal a lot with low-level problems. For example, this story about eventual consistency, since you have a lot of duplication of data, you have to be sure that you have the right expertise in engineers in order to deal with. Otherwise, it will be a mess. And another thing that has to do with engineering expertise is that normally these systems are savage systems. Okay, of course you have documentation, and of course you have insight about the way it works, but people have to be ready to go into the code, to go into the stomach of the system if there are problems, etc. So you need the right experienced engineers that can deal with these problems. Okay, otherwise, again, it's a nice mess. Even if today, since this has happened for a long time, you have solutions like Atlas and the one that we will see for Neo4j, where they start to build levels of transparency in order to make it easier for engineering groups to address their problems without having to build the hammer and then hammer. Okay. And of course, there is the problem of choosing the right combination. So which is the right tool for the right job? And how do I know which is the right tool for the right job? Okay, so these are two questions were a lot popular in the very beginning of the story of NoSQL. Today, there are already best practices, etc., that can be used in order to address problems. So that's something that I said. The problem is non-standardization, and this happens already also today. So before I wrap up, the session. I'm going to wrap up the topic. Conclusion is that anyway we have to deal with classic DBMS as the relational ones and data stores, NoSQL solutions, and we will see here in the course that there are even other solutions that are not still here. We have to understand the features of and the characteristics of the principles of the data management. We have to understand models, languages, and normally see whether the degree of ease of use of the systems. We have to make sure that when we choose such kind of solution, performance and scaling will be there. Okay, if you invest a lot, that's right. We, again, as engineers, you shouldn't be afraid of challenging things, but under the condition that the result really is performant and scales with respect to other classic solutions. If this is not the case, there is no point of suffering. Okay, so this is an important thing to consider. And as I said, well, multi-model databases are the most popular way of dealing with this. And again, before I wrap up, with regards at least to what we have seen theoretically and more or less practically today in the sessions. In fact, you have to think about data management as a spectrum of solutions. And the right data management solution depends on the conditions in which your data arrive. If you have to, and there you will find the data rawness degree, okay? If you have to deal with raw data, the one that you really zip from the source without almost any processing, just the digital content, it's different. The type of solutions you need are different as when you have very curated data collections, okay? That's one thing, and so the rawness degree will guide you with the type of solution that you need. And the other thing is the kind of questions and of operations that you want to perform on top of the data. When you have very raw data, in fact, your operations will certainly be associated to exploration, finding insights. What does the data represent and what does it contain? Insight of the data, and then eventually prediction, foresight of the data. Okay, and once you have worked a lot and with the data and you have curated a lot the data, then you will get to what we start learning in our education, which is relational querying, information retrieval querying, where the data is really curated, and there these solutions are smoothly applied to this type of collections. So for any system and the solution that you have to address, you have to see which are the type of questions, the data, and see within the spectrum where you can place the different challenges imposed by a problem, and then make decisions on the combination of solutions that correspond to your problem. And with this, we wrap up the NoSQL story. As I said, tomorrow we are going to do some practice, not to lose our programming skills, and then we will move forward to other topics. Okay, so do you have comments or questions before we close the session? Yes, please, Francisco.
Yes, hi, doctor. If my question is not related to the theory we just seen, should I do it after?
I mean, let's see if there are other questions. If there are no other questions, you can do it now. Do we have questions about the content? I think nobody has questions about the content. Okay, so excellent. So ask your question.
Yes, well, I think it's like we wanted to ask you if it's possible to, like, you know that sometimes we get the emails like
Yeah.
with the assignments. We just wanted to know if it's possible to just receive like for you to put the assignments and whatever we need to do on Blackboard, because like sometimes it's a little bit confusing because we receive like several emails from multiple accounts of you. So like in order to keep
And
like
you do
everything
not
like
deal with
organized,
many,
I don't know if
and
it's
you do
possible.
not deal with many mails, right? So you have problems to deal with many mails. Is this the issue? Hello. I just want to understand the issue. Yes, I mean, normally what happens is that the Blackboard sends a notification of the assignments. So, yes, I mean, I can stop sending from the Google group email if this bothers you, which is quite impressive with respect to the number of mails normally a normal person can deal with. But if you get confused, the point is not getting confused. Now you have the assignments in the Blackboard. That's something that I know that you are used to it. So you have the assignments here. You see, here you have the deliverables, and in the deliverables you have the assignment, and normally the system assigns a deadline, and the deadline, if I understand well, you have it in somewhere in the activity schedule, I believe. Here you have blah blah. In this thing you have the assignments and the deadlines. That's something that it's already there. I normally use the external system because you I think it's more clear. But if it's not the case, I can stay with Blackboard and make sure only that you know the deadlines. For example, for the ones that I said. Deliverables, you have already the new deadline, and this thing is associated in the with the deadline automatically. So I don't know what you mean that the Blackboard doesn't have the schedule. Yes, I understood that. You get multiple notifications because you get from the Google group and from Blackboard. As I said, I can only use Blackboard. That's right. Just make sure that that you really are aware that you have to hand in the documents. I mean the exercises. And then an accessory comment is that I'm quite surprised that you get confused receiving a lot of mails, because in the real world, you receive a lot of mails and you have to deal with that. But the point is, I mean, the point is being Scholar, and since you are not used to that, I will only use the Blackboard.
Yes, and I think that the problem is not like exactly with you, but like for example, from the university, there's
Yeah,
a newsletter called Utlap Informa, and we get probably like 10, 15
yeah,
emails per
I
day.
do. Yes, I get them too. You know, I have 5 email addresses, particularly the lab one that sends thousands of mails of announcement. I deal with them as you have. This is why I consider this impressive. But since, I mean, for pedagogical reasons, I don't want you to get confused, and I will only use the Blackboard. But this is quite strange situation. From my point of view, I can accept that you have another point of view.
Okay,
Okay,
thank
other, and then, but the only thing that I really suggest is that at least you follow the Blackboard and then Slack, okay? Because otherwise there is no way of contacting you, of interacting with you, and providing feedback in a smooth manner. Because Blackboard is like people say in Mexico, it's Godines, no? Kind of, you know, and the Slack is very, very practical. So at least those two, follow them. Yeah. So for those that arrived late or came back and forth, just be aware that we defined a new deadline for the things that you have to hand in, both in this course and in the lab. Okay, the deadline is the 20th February, and it's already announced on Blackboard. Other
Very
comments,
well.
questions?
Thank you, doctor.
You're welcome. Yes, have a nice day. Have a nice Friday. See you tomorrow.
thank you, doctor. Have a nice Friday.
Thank you. Bye-bye.